class. Please turn to page 13 of your Unit 2 packet so we can talk about 2.6 free fall notes and formulas. So free fall, you might have guessed, is for a falling object like this ball here. It's fallen toward the ground. So free fall is the motion of an object where the only acceleration is that due to gravity, meaning there's no air resistance. Air resistance is when there's air in the room or wherever and you drop something and it slows whatever you drop down. Like if I were to drop a piece of paper, the paper kind of float down because of air resistance. So we're talking about no air resistance. Another name for that, if there's no air, is called vacuum. Vacuum is when there's no air. So free fall is the motion of objects falling, dropping, when the only acceleration is that due to gravity because there's no air. We're in a vacuum. Or at least there's so little air resistance that it doesn't matter. So it turns out in free fall, and you should be taking these notes down, you should be writing this down in your Unit 2 packet. In free fall, objects fall with the same acceleration. All objects fall. I'll put that. All objects fall with the same acceleration. Okay, so it doesn't matter if we drop a bowling ball or a golf ball or a car or a piece of paper. If there's no air resistance, if we're in a vacuum, and the only thing acting on it is gravity, if we're near the Earth's surface, then they're all going to fall with the same acceleration. That acceleration is negative 9.8 meters per second squared. Because it's so close to 10, and because we use it so often, we usually approximate it as negative 10 meters per second squared. And the negative is saying that we're accelerating downward. So 10 meters per second squared downward. This is true for Earth only. It would be different if we were on the moon or if we were on Jupiter, something like that. Alright, on your MCAS equation sheet, which we got recently, the acceleration due to gravity is listed there, and it's called g. Because it's a constant and we use it so often, it gets its own letter, g, for gravity. And that's the acceleration due to gravity. And we say that g is this 10 meters per second squared. So the acceleration is really this g, but downward. We're not really going to use the letter g for right now, but we will use that the acceleration is negative 10 meters per second squared. So that means anytime an object is falling, we get to use this acceleration. Anytime an object is dropped or falling, we automatically know this acceleration. Even if it doesn't tell it to us, we know it just because it's dropping. Okay, so let's scroll down here. Remember, we got those equations for acceleration. Number 1 and number 2, we're going to do in class, or we're going to talk about it in class. Here's number 3. Tom drops a 5-kilogram bowling ball off of a cliff. The bowling ball was initially at rest, then it fell for 3 seconds. Halfway through the drop, what is the acceleration of the bowling ball while falling? Okay, so we're dropping something. It's falling. That means the acceleration is negative 10 meters per second squared. That's true halfway through the drop. It's true at the beginning of the drop. It's true at the bottom. It's true the whole time the object is in the air. We know the acceleration is negative 10 meters per second squared. Part B. What was the bowling ball's final velocity right before reaching the ground? So we're not talking about when it hits the ground and it stops. We're talking about right before it hits the ground. Alright, so let's list our given information. Tom drops 5 kilogram bowling ball. Alright, the minute we see the word drops or falling, it fell, we get to write the acceleration is negative 10 meters per second squared. Notice again, it doesn't say that anywhere in the problem, but what it does say is it's dropping or falling, so we know that's true, because that's for free fall. The acceleration is negative 10 meters per second squared. It's a 5 kilogram bowling ball, so that's the mass is 5 kilograms. The bowling ball was initially at rest. Rest means it's not moving, means the velocity is 0. It says it's initially at rest, that means the initial velocity is 0 meters per second. And it fell for 3 seconds. Seconds would be time, so delta t is 3 seconds. The unknown is what was the bowling ball's final velocity? So we're looking for VF. So then we look at our MCAS equation sheet. We look for an equation that has VF in it. And I've got two listed up here. So both of these have VF in them. And then let's look at this one because it says VF equals VI. Do we have VI? We do. It's 0. A. We have A. It's negative 10 meters per second squared. And delta t. We have delta t. It's 3 seconds. So that's the formula we can use. VF equals VI plus A times delta t. Now all we have to do is plug in. So VF equals 0 plus negative 10 times delta t is 3. So negative 10 times 3 is negative 30 plus 0. VF is negative 30 meters per second. Now notice our number is negative. Why is the velocity negative? Because we're moving downward. So it's important that we have that negative sign when we put in the acceleration, because then later we know the velocity is downward. So that's the object's final velocity right before it reaches the ground. Let's turn to the next page now, page 14. At the top of page 14, we're going to write an equation. It says if an object is accelerating, for example falling, the displacement delta x, initial velocity vi, change in time delta t, and acceleration a are related in the following equation. Delta x equals v initial times delta t plus 1/2 acceleration times delta t squared. Alright, so I want to point out a couple things here. This is vi times delta t, and this is 1/2 times a times delta t squared. The only thing that's being squared is delta t. Only the time gets squared, not the acceleration or the 1/2. So if you know the time, you square that and then you multiply by a and 1/2. So let's try to use this equation. It says Tom drops a 5 kilogram bowling ball off a cliff. The bowling ball was initially at rest and it fell for 3 seconds. How far did the bowling ball fall? Alright, so it looks like the same problem as before, except we're asking for something different. So Tom drops a 5 kilogram bowling ball. It drops, so we know the acceleration is negative 10 meters per second squared. Anything that's falling around Earth is going to have negative 10 meters per second squared as the acceleration. It's a 5 kilogram bowling ball, so the mass is 5 kilograms. The bowling ball was initially at rest. Again, that means VI equals 0 meters per second. That's a velocity initial, 0 meters per second. And it fell for 3 seconds. So that's delta t, it's 3 seconds. How far did the bowling ball fall? How far? So anytime we see how far, we're going to write delta x, not d. We're not writing distance, we're writing displacement, not d for distance. We're writing delta x for displacement. Now we look for an equation on our equation sheet, and because I've written this right above, it's probably that we're going to use this one. Let's check it out. It has delta x. Good, that's the unknown. We need that. Vi, we know. Delta t, we know. A, we know. And delta t, again, we know. So that's our equation. That's our formula. Now we just have to plug in. Delta x equals 0 times 3 plus 1/2 times negative 10 times 3 squared. Delta x equals 0 times 3 is 0 plus 1/2 times negative 10 times 3 squared. Well, 3 squared is 9, so let me write that in. 1/2 times negative 10 times 9. Delta x is 1/2 times negative 10 is 5 times 9 is 45. But it was negative 10, so negative 45 meters. What does that negative sign mean? Well, if we're talking about displacement and something falling, the negative is saying it fell 45 meters downward. So that's our answer. I'll include the down in my box. There we go. Alright, again, keep that negative sign with the acceleration, because then at the end that means, if you get a negative sign, it means it went down. Let's look below that. It says, if an object is accelerating, for example, falling, and the time is not known or desired, the displacement, initial velocity, final velocity, and acceleration are related in this equation. Vf squared equals Vi squared plus 2a delta x. So that's velocity final squared equals initial velocity squared plus 2 times a times delta x. Let's try to use this one. Tom drops a 5 kilogram bowling ball off a cliff. The bowling ball was initially at rest and it fell 45 meters. How fast was the bowling ball going right before it hit the ground? It's dropping, so the acceleration is negative 10 meters per second squared. Acceleration is negative 10 meters per second squared anytime it's falling or dropping. That doesn't mean if there's like a car accelerating that it's got that acceleration, or somebody's running. There's only for things that are being dropped or falling. The mass is 5 kilograms. The bowling ball was initially at rest. Vi is 0 meters per second. And it fell 45 meters. Careful there. Delta x, if it fell, is negative 45 meters. The unknown in this case, how fast was the bowling ball going? Vf. The formula. We look for one that has Vf. Here, this one has Vf. Do we have a Vi? We do. Do we have an A? We do. Do we have delta x? We do. So our formula, Vf squared equals Vi squared plus 2a delta x. Now we plug in. Vf squared equals 0 squared plus 2 times negative 10 times negative 45. Vf squared equals 0 squared is 0. 2 times negative 10 times negative 45 is positive 900. So VF squared equals 900. It's a good thing it's positive because the next thing we need to do to get VF alone is we take the square root of both sides. Because we have VF squared, we need to get rid of that squared, so we take the square root. And you can do that on your calculator. It's the button that looks like that. So VF is the square root of 900. The square root of 900 is 30. And it's meters per second. Now, how fast was it going? Technically, square roots, it's positive or negative. So we have to determine, we know it's going downward. So it's going to be negative 30 meters per second, or 30 meters per second down. So that's our answer. Okay, you can turn the page to page 15. You are going to do these problems, 6 and 7. You're going to do those. But number 8, you can cross out. We're not going to do that problem. So we're crossing out 8. You will do 6 and 7 though. And then if you turn the page to page 16, I think, you're going to do number 9, but on page 16, you're going to cross out number 10. Okay. So you're going to do number 9, you're doing 6 and 7. Enjoy yourself. And I will try to turn this video off.